Okay, we're finishing off lesson 7 here. We were doing like classic matrix operations before. Now we're going to get to a special kind of thing you can do with matrix operations, which is called a determinant. Now I'm going to give it a definition of a determinant. I'm going to show us how to do it. And you might think like, man, this is just, we're just moving these numbers around. Like, what's really the point of it? The point of it is to come into the rule we do at the very end. And this rule is actually the reason we're in the system of equations module in general. Um, I guess that's the short answer. A long answer, determinants have like wild uses in outside higher level math classes. But for now, we're just going to show the definition. We're going to show how to use it and then move on from there. All right. So determinants, given any any matrix, we're going to start with a 2 by 2 matrix. B, C, D. So these can be any numbers. Like I can have this number be 5, 4, 3, 11, or something like that. That's a matrix, right? But given any matrix A, we have the determinant of A is taking these numbers and multiplying them and subtracting them in a certain way. So determinant of A in this case is AD minus BC. It's this side minus this side, right? If I had, let's do this minus this, right? So I'll let me get that. Or I can say this diagonal minus the next diagonal. That. Those are going to be numbers, so the determinant of A will become a number. So again, whenever I write A, when A is a matrix, say A is like what we say is a matrix there. If I do these lines, that means find the determinant. It's kind of like absolute value, but it really means determinant when we're working with matrices. I'll say again, the determinant of A, that is what I think in my head when I see this symbol. I'm like, oh, that's the determinant of A. And I know when to find the determinant of A, I use the formula AD minus BC. When these are numbers, I actually multiply and subtract those numbers accordingly. Okay, so it's not too bad. I'm going to say I have A is this matrix. The determinant of A, right, is this diagonal minus the next diagonal, right? So I just do that. I have 3 times negative 2 minus 1 times 4. Or 4 times 1, I guess that's how I did it in the formula, but 1 times 4, 4 times 1, same things. I'm doing this diagonal and this diagonal, multiply them together, subtract the 2, I get what? Negative 6 minus 4 or negative 10? It's that easy. Determinants shouldn't be too tough once you know how to do it. It's tough just to remember this formula because we don't really have a grounding on the use of it yet. We'll do a couple more here. Find the determinant of B when B is equal to 4, negative 1, 8, negative 2, right? As a matrix. This is a matrix, so when I say determinant of B, that is equal to, this is the symbols, or the set of symbols I use to find the determinant of B. And again, I do multiply diagonal minus multiply diagonal. So 4 times negative 2 minus negative 1 times 8, like that. Again, you can just flip them however you want, as long as you're multiplying the right numbers together, right? I like to do highlight stuff, right? You can kind of see me do the highlight stuff. This is just to create our connection here. What do I have? I have negative 8 minus negative 8 or 0. Negative 8 plus 8 becomes 0 here. Okay, given C and D, find the determinant of C plus the determinant of D. So let's find the determinant of C first. I won't do any highlighting anymore. I have negative 3 times 5, which is times negative 5 minus 6 times 0. What is that? That is 15 minus 0, so 15. The determinant of D is, again, I do -5 times -1. It's okay to write it out. I'm writing it out. You can write it out too. Minus 6 -1. Like that. Or, I'll stay consistent because I have to do at C times D, right? So, or C times B, right? So I'm gonna go like that here. Either way, it's this diagonal is the second number. So I have what? 5 plus 6 or 11. And we're trying to find the determinant of C plus determinant of D plus determinant of D. That is 15 plus 11 or 26 as our full answer here. So kind of cute. You might have like 1 or 2 lessons in your Alex homework on this. So just look out for it. The key is this formula, right? If you know how to do the formula, you just apply the formula. It's a nice little addition subtraction, and life is good. Why do we need this? Why do we like determinants? Because there's this really, really magical thing called Cramer's rule here. Cramer's rule is a way to solve systems of equations, which is where we're at, right? We're talking about systems of equations here. And it's kind of like the third method, right? There was um, elimination, there was substitution, substitution. Now we do Cramer's rule. And something nice about Cramer's rule is it's the same process no matter what, so long as you just know how to use a determinant. Determinants are something you might have never seen before this class. That's why they never teach you it this way. But this is really like the hammer that solves everything. And it's kind of nice that once you figure out determinants, I'll say. And I have the rule written here. So I would recommend pausing the video to just like copy this down, put a little star around it, like box it, do whatever you need to do. Be like, oh, this is how you do Cramer's rule. And it's kind of an OP rule, not gonna lie. And it involves finding 3 determinants. 3 determinants means we need 3 matrices, right? We need 3 of these and then finding the determinant, right? I say we can find determinants of things when they look like this. It's like, I don't see a matrix here. I see like 2 equations. Ooh. What does it mean to, for one, find the determinant of the matrix with variable coefficients? That looks like nonsense to me. Well, I have variable coefficients here. If I like put a little, let me put a little like 1, 1, 1 here. I see I can create a matrix, right? It looks like I can create the matrix. Um, let me put these on here like that. So D is like the matrix, and then when I take the determinant of that matrix, that's what we have here. That'll make things a little bit cleaner for us. Even though the formulas might look weird, let's just kind of go with it. What is D going to be? D is going to be the matrix 2, -1, 1, 1. That is from the coefficients, the numbers in front of the variables. I created a 2 by 2 matrix. Well, let's take the determinant of that. That is 2 times 1 minus 1 times -1. So 2 plus 1, that's equal to 3. Here. And I got that from those 2 front numbers. Now, what is dx as a matrix? Dx is going to be, we change whatever the x column is with the answer column. So instead of having 2, 1 in this column, I'm going to have 6, 3, because the x column is replaced by the answer column, and then I have the y column be the same. So it looks like I changed this to right here as if this was 6, 3, and I created a matrix like so. So let's go bam, bam. That 6, 3 is going to move around a little bit. Let's take the determinant of this. And right, that x is just a subscript. It's a notational thing. If it looks weird, it's like, man, what is this dx here? I'm just using it. It's a matrix where I'm doing something with the x's, x column. That's how we show that notation. People change notation however they want, though. Either way, I know how to find the determinant of a matrix once I have it. minus 3 times negative 1. And that is what? 6 minus, or 6 plus 3, or 9, right? And then lastly, I do the same with my y's. I leave my x column the same, and then I change my I change my y column to the answer column. That's what dy is. So how do I find this? The determinant of this is 2 times 3 minus 1 times 6. And that is going to be 6 minus 6, or 0 here. Now we automatically get a solution. Solution. I just use this formula from Cramer's rule. X is equal to dx over d, which is 9 over 3, or 3. Y is equal to dy over d, which is 0 over 3, or 0. As a point, xy is equal to 3, 0. Like that. That is wild that works, right? How is it? I mean, you might be like, man, I just don't care about math or something. But like, isn't that crazy that this seemingly random rule or random property called the determinant can be used to solve problems? You might not even believe it. I recommend, one, you can plug these numbers in, right? If I plug in 3 for x and 0 for y, 2 times 3 is 6. That works. 3 for x, 0 for y. 3 plus 0 is 3. That works. If we did do the elimination method here, right, I could have added these down. Let's check, see what happens when I add these down like so. I'm going to have 3x is equal to 9, or x is equal to 3 when I divide by 3, right? And I could have I plug the 3 back into here, and I get what? 2 times 3 minus y equals 6. 6 minus y equals 6. Okay, yeah, I get the same thing, right? I subtract the 6 over, negative y equals 0, or y needs to be 0 there as well. So doing elimination method gives me the same answer. So this seems to be pretty consistent. I'm going to make the argument why Cramer's rule is nice. Let's move down to here. Now we have another problem. 5x minus 7y equals 4. 13x plus y equals 8. Now, if you try this in elimination or substitution method, it would probably be sucky. But let's just do Cramer's rule, right? Cramer's rule. We're going to have a matrix D, which is these numbers, right? 5, negative 7, 13, and 1. I take the determinant of D, which is, oopsies, 5 times 1 minus 13 times negative 7. Oh my gosh. I don't know what 13 times negative 7 is off the top of my head, do I? Plus 91. What is this? 96? Here. I don't know it off the top of my head. So I'm not gonna be a hero here, right? 13 times negative 7, negative 91. Oh, so 5 minus negative 91, that does become 96. Okay, we're good. We're good here. Let's see if I might need this for the next one. Dx is changing the x column, right? This now goes in the first column now, because I'm changing the x column. The determinant of dx is equal to 4 times 1 minus 8 times negative 7, which is 4 plus 56, 60 here. And lastly, 5 and 13. And then I change this to 4 and 8. My next column, my y column for my dy matrix is going to be 4, 8. And then I find the determinant. This is going to be 5 times 8 minus 13 times 4. I'm like, sometimes I use parentheses, sometimes I don't. You know, it's the same thing as like 13 number times 4 number, right? That's all the same. What is that? 40 minus 52, so negative 12. So now I get the answers. X is equal to my dx over d, which is what? Negative 12, no, 60 over 96. Y is equal to dy over d, which is equal to negative 12 over 96. Now, these can be reduced, right? I can see it, right? I think 96 can be divisible by 12. So this can be reduced if I like divide by 12 on top and bottom. That equals what? Negative 1 over 8. And similarly, if I divide by 12, right? By reducing this fraction, 60 divided by 12 is 5. Oopsies. 60 divided by 12 is 5. So I have 5 over 8. So I have x equals 5 over 8, y equals negative 1 over 8 as my answer. Fractions. Notice this answer gives fractions, and that's going to be the right answer here. However, we never had to really work with the fractions. Really, all we needed to do was work with the matrices, and then we got a fraction at the very end. Sure, we needed to reduce it, but not working with fractions until like the very, very last step where it's just reducing, that's a lot better than working with fractions the whole time. So this is going to be our star problem here, this next one. So I want you to use Cramer's rule on this. And then I want you to give a sentence. Why would substitution or elimination suck here? There's going to be a reason why it would suck. And honestly, I recommend try using substitution or elimination. See what would happen when you do substitution or elimination here. And you're going to be like, oh, goodness, this is like, ugh. Why is it going to be a lot? Just try it, but solve it using Cramer's rule first. And all right, that is it. Thank you all for watching. Yeah, matrices and like determinants and Cramer's rule, they're a little weird, but this is a useful reason for using them, right? We just saw a bunch of application problems. If we just apply Cramer's rule to all those application word problems, we get the answer, not necessarily right away, but it gives us the answer in a very consistent manner. Thanks for watching, guys.